Chapter 1.4 is the real number system. So before we get into different sets of numbers, we just have to describe what a set is. So a set is just a collection of objects whose contents can be clearly determined. And whatever's in the set, the objects in the set, are called the elements of the set. And the way that we represent a set are with the braces or squiggly brackets. There are a couple different ways we can actually represent a set. The two ways that we're going to do it are either going to be the roster method or the set builder notation. So for the roster method, what this does is just lists the elements out and uses commas to separate the elements. So if we were looking at the natural numbers and we wanted the set of natural numbers, also called the counting numbers, it would be the set of numbers 1, 2, 3, 4, 5, 6, 7, and so on. So the way that we denote it is with these squiggly brackets, and we put this little ... afterwards to let us know that it continues in this fashion, in that pattern that's pretty clear. So that ... is actually called an ellipsis. So that's an ellipsis. So that's the roster method, just listing out the elements. The other method is the set builder notation. Set builder notation is a little bit more complicated. The elements for set builder notation, the elements are not listed this time, but they're actually just described. So this is what it's going to look like. It has the squiggly brackets around it. And the way that we read it is this first part right here is read as the set of all x values. We have this vertical line next to it. The vertical line is read as such that. And then in this case it says x is a counting number less than 6. So these are actually the same sets from this first one and this one. Just one's in the roster method, the other's in set builder notation. So this portion right here is just the description. And this can be done in various different ways here. So we have the squiggly brackets or the braces around it, so you know it's a set. And you read it like this with that vertical bar and set builder notation as the set of all x values such that whatever the description happens to be. So not every set has elements in it. Sometimes sets can have absolutely nothing in it. So that's different from having the element of 0 in it. If a set has no elements, it's called the empty set or the null set, and it's represented by this symbol right here. It looks like it's a circle with a slash through it. So that represents the empty set. Another way it gets represented, which in my opinion doesn't look as nice, is squiggly brackets, the braces with just nothing in it, just completely blank. Okay, so let's get to the next thing where we describe several really important sets of numbers here. So for the first one, let's look at the natural numbers. So we've already done this. The set of natural numbers is going to be 1, 2, 3, 4, 5, 6, 7, and so on. We denote this with a capital N with that little double backbone on the end. So this is the set starting at 1, just positive integers here. Okay, next thing for whole numbers. Whole numbers is going to be denoted with a W, and we put the little double backbone over there. Doesn't really matter too much. Whole numbers are going to be the natural numbers with 0 included. So 0 is a whole number. What we can actually say is that the natural numbers are a subset of the whole numbers because they're contained inside the set of whole numbers. Next, for integers. So integers are actually denoted with a Z. Put double backbone right there. So the set of integers are going to be negative and positive whole numbers. So the way that we can denote this is put an ellipsis to the left, and then maybe say -5, -4, -3, -2, -1, and 0, 1, 2, 3, 4, 5, and then ellipsis again. Okay, so that's how you kind of define the set of integers, and then you can use that ellipsis on the left saying it's going towards negative infinity over there. So next, hopefully those ones aren't too complicated here. For the next thing for rational numbers. So rational numbers are given a Q. So that represents the set of rational numbers. So rational numbers, I was using roster method up here. For rational numbers, I'm going to use set builder notation. So I am going to say it's the set of all values, which we can call A over B. So it's the set of all ratios, it's the set of all fractions. A divided by B, where A and B are integers. So they're positive or negative whole numbers. So for examples of this, we could have something like just straight up -5. -5, that we know that's an integer. We can rewrite that as -5 over 1. -5 and 1 are both integers, so -5 is a ratio of integers. Hence the name rational numbers, ratio of integers. So these sets are kind of getting absorbed into the one above them for now. So natural numbers are a subset of whole numbers, which are a subset of integers, which is a subset of rational numbers. So another example for rational numbers could be 2/3. So 2/3 as a decimal, so it's a rational number because it's a ratio of two numbers where the numbers numerator and denominator are integers. As a decimal, this would be 0.6666666 repeating forever. So we can say 0.6 repeating. So repeating decimals are actually rational numbers. Even though they're not terminating decimals, they're repeating. Repeating decimals can be represented as a rational number, so a fraction of two integers. And that may be something as simple as 2 over 5. 2 over 5 as a decimal is 0.4. So terminating decimals are also rational numbers. Those are probably a little bit more obvious. Okay, and then for the next one, for irrational numbers. So irrational numbers, we can denote this with a capital I. I'm just going to do a cursive I. And for irrational numbers, essentially these are just going to be not rational numbers. So this means it's going to be any number whose decimal representation is neither terminating nor repeating. So it's a little bit less obvious until we do some examples here. Let's do some examples. So I'll do the two most commonly used examples for these ones. Radical 2. So that's the square root of 2, which we'll get dealing with square roots more. If you plug that in the calculator, it'd be approximately 1.41422135 and so on. That's going to keep on going. It's going to be non-terminating and it's never going to repeat. So that's going to be an irrational number. So another one is going to be pi. Pi is an irrational number, and pi is approximately 3.141592 and so on. It keeps on going forever and it's never going to repeat itself. So we cannot represent either of those numbers as a ratio of two integers. Something like square root of 3, square root of 5 would also be irrational. Okay, for the last one, for real numbers is going to pretty much sum up this whole thing. Real numbers is going to be denoted with the capital R. So real numbers are essentially every number that you can think of except for imaginary numbers or infinities. So it's going to be the set of all x's such that x, so I'm doing this in set builder notation, x is rational or irrational. So every number on this page that we wrote is a real number. Okay, let's do an example. So let's consider this set of numbers here. So we have this set of numbers. We have -7, -3/4, 0, 0.6 repeating, radical 5, pi 7.3, and radical 81. So we're going to go through and list the numbers in the set that are natural numbers, whole numbers, and so on. So let's look at natural numbers first. So going through the set, we know the set of natural numbers are positive whole numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So -7 is not a natural number. Neither is -3/4, neither is 0. The only one that is secretly is radical 81. Radical 81 actually equals 9. So since that equals 9, 9 is a natural number. So that means radical 81 is also a natural number. So next for the whole numbers. So we already know that for the whole numbers, we know that radical 81 is also going to be a whole number because it is, natural numbers are a subset of whole numbers. But for whole numbers, we're looking for the numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on. So we actually have 0 here. So 0 is a whole number, and so is that radical 81. So there's nothing else in there that would be a whole number. So next for integers, integers are positive and negative whole numbers. So we have -7. So -7 is going to be an integer. And so is 0, and so is radical 81. And that's it for the integers. Now for rational numbers, so now it's going to be getting a little bit bigger. Rational numbers are any numbers that can be written as a ratio of two integers. So I'm just going to kind of go left to right here. So -7 works, -3/4 works. So -7, -3/4. So does 0. We can write 0 as 0/1. Those are both integers. 0.6 repeating, we can write that as 2/3. Radical 5 is an irrational number. 7.3 we could actually write as, it's the same, it's a terminating decimal, so we don't have to actually show it. Terminating decimals are always going to be rational numbers, but it's also equal to 73/10, which are both integers, so that works. And so does radical 81, because it's equal to 9 again. Okay, and then for irrational numbers, we have radical 5 and pi. So radical 5, pi is always irrational. And for real numbers, that's going to be everything. That's going to be rational numbers and irrational. So I'm just going to quickly jot down both sets. So -7, -3/4, 0, 0.6 repeating, radical 5, pi, 7.3, and radical 81. Okay. So for the next thing, so those are the sets of, the main sets of numbers that we'll be using. So for the next thing, for the real number line, the real number line is just essentially a one-dimensional graph. It's a graph used to represent the set of real numbers. Okay, so here's what the number line looks like, just like the normal number line that you're obviously used to. So we have 0 in the middle, and then it goes positive numbers on the right, and it has negative numbers on the left. Okay, and then the numbers increase from left to right. So it's going towards negative infinity, and it's going on the left, and then towards the right it's going to positive infinity. Okay, let's just do this last example. Let's graph each rational number on the following number line. So we have negative 3 halves, negative 2 thirds, 0.5, 1 1/3, 23/8, 3.25, and 4. So we have a whole bunch of different types of rational numbers here. So for the first one, for negative 3/2, so negative 3/2, this is an improper fraction. It's one of them where you probably should know the decimal representation or the mixed number representation off the top of your head because it pops up a lot. Negative 3/2, if you don't, you would remember, if you wanted to put it as a mixed number, you would divide it. You would do 3/2, 3 divided by 2. This would give you negative 1 1/2. So this is negative 1.5. So that's going to be right here. So that's negative 3 halves. Negative 2/3. Negative 2/3 is 2/3 of the way to negative 1, or negative 0.6 repeating. So that's going to be right here. It's negative 2/3. Next, for 0.5, 0.5 is obviously 1/2, halfway to 0, between 0 and 1. So that's going to be right here. For 1 1/3, 1 1/3 is going to be 1, and then adding another 1/3. So that's 1/3 of the way from 1 to 2, so about right here. 23/8, so this one might not be as obvious, so let's do some little division. Let's turn it into a mixed number. So 8 goes into 23 evenly twice. 2 times 8, 16. We subtract, we get 7. And then that's going to be our remainder. So 23/8 is actually equal to 2 and 7/8. That's probably a little bit easier for us to visualize here. 2 7/8 is going to be about right here. So 2, well, I'll write it as 23/8 actually, because that was the original. And for 3.25, 3.25 is going to be here. And lastly, for 4, that's going to be right on 4, obviously. Okay, so I'm just going to draw little arrows to each one, just so we don't get confused. So that is actually it for section 1.4.